Hi everyone, welcome to Unit 6. So in Unit 6, the whole premise of our work is around estimating for the population parameter, whether that's a proportion, a percent, or a mean. And our first line of defense for estimating that population proportion or mean is by using a confidence interval. And so before we dive into actually calculating confidence intervals, we're going to learn some of the basics, like what does it look like? How is it structured? How do we interpret it or explain what it means? And so that all starts with what's called a point estimator. A point estimator is a one number estimate that we use in order to estimate for a whole population. And so a point estimator is that statistic that provides the estimate of a population parameter. All right, the actual value of that statistic from the sample is called a point estimate. Okay, so our point estimator for the population mean is going to be the sample mean. And our point estimator for the population percent is going to be a sample percent because it comes from the sample and it's our estimate. All right, so here's an example. Imagine that you see that Hilliard claims that their students have an average ACT score of 22 on the district website. You decide that you want to confirm that this is true by running your own test. You know that obtaining this may be time consuming and difficult, so you decide to take a random sample of 40 seniors from each school and find the average of their scores to be 24. So that seems higher even than what was claimed. So in this case, we are attempting to estimate an average, so a population parameter, which would be the population mean. And so to do that, we are using a point estimator, which is the sample mean ACT score. And the value of that sample mean ACT score is our point estimate, and it would be a 24. Okay, so point estimate is the actual value. Estimator is what we are actually finding from the sample. And so this translates eventually to an interval of two values that we call a confidence interval. And so here is what that could look like. Let's say we calculate a 95% confidence interval for the population average ACT score, and we find a range of values of 20 to 28. Okay, we are going to do a lot of interpreting as we're calculating, and so that's sort of why we start with that in this first example or set of notes. So to interpret this confidence interval, we would say we are 95% confident that the population average ACT score is between 20 and 28. All right, now anytime you interpret a confidence interval, it should look like that. You'll have your percent that you are confident, that's called the confidence level, and then you will list what you are estimating. So in this case, that was the population average ACT score. We should always say population, so it might be the average calories or the average speed or the percent of students who say yes or something like that. And that will always be between the two values that form your interval. Then when we interpret that 95% level, we say that 95% or whatever percent you are interpreting of all samples will produce an interval that includes the population average. Now, in this case, we could say average ACT score. It could be just the population average. I'm not very picky about how detailed you get there. The key thing is that that percent tells us what percent of any sample you take that is the exact same. So that percent of samples of 40 seniors from each school will produce an interval when you calculate their interval that correctly captures the actual average ACT score for all of Hilliard seniors. All right. And so once we have this interval, we've got some properties. Every confidence interval starts with that statistic, that point estimate, and then you add or subtract two numbers that you multiply. The first is a critical value. We're going to really focus on that critical value tomorrow. It relies on the confidence level. And then the second is the standard deviation of that statistic, which you'll use formulas for that you're used to using from last unit, Unit 5. Okay, the margin of error, that's a really important term, and hopefully it's one that you have seen out in the world prior to this lesson today. The margin of error is what you add and subtract to and from your point estimate, your statistic, and it is the critical value times that standard deviation. All right, now, not every confidence interval is a 95% confidence interval. Sometimes they're 98, sometimes they're 99, sometimes they're just 90. It really depends on what you choose as the statistician for your percent. And so let's talk just briefly about that critical value. So it depends on the confidence level. Okay, so the bigger percent you choose for your confidence level, the wider the interval is going to be. It's going to have a wider range of values, which means that critical value will be larger. All right. Also, we have to remember that our standard deviation depends on your sample size. We talked about that also in the last unit. The bigger your sample, the smaller the variation or variability, so the smaller the standard deviation, right? So that margin of error shrinks or gets smaller, right? So this number, critical value times the standard deviation, gets smaller if you decrease your confidence level, that percent, and if you increase your sample size, right? Because that shrinks the standard deviation. And so here are two examples. These were produced from the exact same point estimate. You'll notice that the center point looks to be about 240 or 241-ish for both of them. But then the 95% confidence level is much wider, spanning from 230 to 251, than the 80% confidence interval, which spans from 234 to 248. So that's a tangible, a visual example of how that margin of error is bigger when we have a higher confidence level, a bigger percent. All right, and so the last thing we're going to talk about today is an important checklist. So in order to calculate any confidence intervals, you have to know all three of these things are true. You have to have a random sample. You have to have a normal distribution, so your sampling distribution has to be normal. This means for sample means, so if you are calculating X bar, that N has to be greater than or equal to 30, or that the population has to be normal, but we probably won't know that because we don't know much about the population in this unit. And then for proportions, if you're using p hat, we have to know that n times p is greater than or equal to 10, and that n times 1 minus p is greater than or equal to 10. Both of those are what we used back in Unit 5 to say that our sampling distribution was normal. So I'm hoping that's not groundbreaking or crazy new for you. And then the last thing we have to know is that our trials are independent. And so in order to say that, we use that 10% condition that we used in the last unit, where we have to know that our sample N has to be less than 10% of the overall population. So if we think back up here to our Hilliard claim, we took a random sample. So we checked that off the list. We were calculating the average, the sample mean, and so N had to be greater than or equal to 30 in order to be normal, and it was. Okay, and then we had to have independent trials. Is 40 less than 10% of all seniors in Hilliard? Well, I guess it'd be at each school. And it is, right? I think we have close, it's very close to 10%, but it should be about 10% or a little less even. Okay, so in this case, our setup checked off those 3 requirements for us to be able to calculate a confidence interval. Okay, so hopefully that set you up to do your exit ticket. Good luck on that, and make sure to double check my key so that you can see how you did.